All right, section 4.2 is going to feel like it's not very connected to or related to section 4.1. I promise by the time we get through 4.3 and 4.4, we will merge them together and you'll see the relationship between them. But right now it's going to feel very disconnected. Right? The title in this section is Sums and Sigma Notation. And what we're first going to do is to introduce the notation that we're involved in doing the problem. Okay? So just allow yourself to feel a little uncomfortable with the notation for the moment. Be okay with it. Write all the details down, and then I'll talk to you about what this is actually doing. All sigma notation is a shorthand way of writing a bunch of things added together. That's all it is. Okay? Mathematics, we like efficiency. We like to be able to do things with as little writing, as little notation as we can. And so you see shorthand notation in mathematics all the time. This is one of those places. Shorthand notation. So the way that we would express adding a whole bunch of terms together, A1 through AN, especially if there's a relationship that defines how A1 to AN are actually described, right, is we write this sigma, and sigma just means add things together. The value at the bottom tells you where you start, the index I equal 1. The value at the top, N, tells you where you end. You start at 1, you end at N. So if it says start at 1, end at 4, 1 to 4, it just tells you you've got 4 terms, A1, 2, 3, and 4. Okay? Where you start, where you end. And then, yeah, the lower and upper bounds. Okay, I think I got it all. You ready to try one? Okay. So what we're going to do on the next problems is going to feel like you're not in calculus. Does that sound good? Sure, why not? Okay. Here we have some notation. We're going to get a little bit more comfortable, a little bit more familiar with the notation. Where does it say we're going to start? At 1. And where does it say we're going to end?
6.
At 6. And it says we're going to find the sum. Okay? So we're going to figure out what the sum is. But we're going to figure out the sum by first figuring out what the values are that we're supposed to be summing. So the first thing we're going to do is we're going to find A sub 1, because that's where we start. A sub 1 means take the number 1 and plug it in for I. So you're going to do 3 times 1 minus 2. What is 3 times 1 minus 2? That's 1. A2 means I'm going to do what? 3 times 2 minus 2, which is going to give me what? 4. A3 means I'm going to do what? 3 times 3 minus 2. Does this feel like algebra? It should. This feels like doing algebra, like college algebra or even lower level than that potentially, depending on where you saw the first function notations. What is 3 times 3 minus 2? 7. I'm going to do one more and then we're going to talk about the last two. A4 would be 3 times 4 minus 2, which gives me what? 10. How many more of these do I need? 2. I'm supposed to go to A6. Can somebody tell me a way that I could find A5 and A6 without really putting a 5 and a 6 in? Adding 3. If you notice the pattern, whoops, 16, there we go. If you notice the pattern here, by all means use it. This is what's called a geometric sequence. I'm sure you've seen that before, maybe not anytime recently. It says what, I'm sorry, not geometric, arithmetic sequence. Yeah, I got the word wrong there. Arithmetic sequence, it means I'm adding the number to get to the next term. In this case, it's the number 3. That number 3 would actually also be called a common difference from geometric, or from an arithmetic sequence. But we didn't finish the problem. What were we really supposed to do with all these numbers? Find the sum. We're supposed to add them together. So this is supposed to be 1 plus 4 plus 7 plus 10 plus 13 plus 16. Okay, so what happens when I add those numbers together? You're welcome to grab a calculator to do it more quickly. I know you know how to add, so it's not a problem. I think Mackenzie's got it for us. Or Fernando. No, not Fernando. Oh, Josh does. Did you get it, Josh? 51 sounds good. Is that what you got, Mackenzie? Yeah? Okay, great. So the sum is 51. All right, so let's pause for a moment and ask the question that you're probably, some of you at least, dying to ask. What do I really have to show on this problem? And you showed a lot of stuff that looked like algebra that I can do maybe in my head. Do I really have to show that? And the answer is no. But what I do want to see, at the very minimum, is I want to see this list of numbers. And the reason I do is because that way, if you get off somewhere and your answer is off, I know why. Oh, they just did something silly where they added 2 at one of the places, and then now their answer's off by 5 at the end because they added 2 in this place. You know what I'm saying? I can give you partial credit if I can see where the mistake is, and I can't see inside your head to know if the mistake happens there. The other problem in general is that if you just put the answer, then I have no idea if you did it using a calculator, because your calculator can do this problem flat out, can do it. Or a back of a book, or a neighbor, or something like that. So this lets me see a little bit of the work behind how this actually processed. Make sense? All right, let me show you another cool feature. There are some formulas that allow us to simplify the process here. Okay, so if you had to add like 50 of these together, that would not be fun. Even if you could find most of them in your head. Right? I don't want to add 50 of these together. That would, honestly, that'd be a waste of my time. It'd be a waste of your time. But we may sometimes actually need to know what happens or what we would get if we added 50 of them together. So what could we do? Well, there's actually several formulas that allow us to shortcut the process. So these are called summation formulas. Some of them have names. The first 3 have names. The first one, we can actually talk about where it comes from. So the first one is a constant. So what happens if you add a constant together n times? So let's actually give it some meat here and say I have the number 3. How could I do it easier to say I want to add 3 plus 3 plus 3 plus 2, 50 times? What would I do? 3 times 50, right? It's repeated addition, which is the same as multiplication. So if I simply have a constant, the same number added together a whole bunch of times, all I have to do is to multiply that number times however many numbers I'm supposed to have. I gave the example 50. In this problem, they're using n, I mean, not this problem, but this notation, they're using n as my top value, so there are n values. Are we good with that? Okay. All right, the next ones are not the case where they're the same. Everything else means I'm adding different numbers together. So let's take a look at what number 2 does. Number 2 adds 1 plus 2 plus 3 plus 4 plus 5 all the way up to n. That's what I'm supposed to be doing, right? I want to show you where this formula comes from because it's very easy. Let me give you the thinking behind it. We'll just write it to the side. If I were to add 1 plus 2 plus 3 all the way up to n, and let's give this a name. This is the sum S that I'm looking for. Okay? I want to add this list to itself, and I'm just going to write it in backwards order. N plus, what would the number be before n? N minus 1. What would the number be before that? Yeah, n minus 2. And I would go all the way down to what? Where does it stop? No, it doesn't stop at n minus n. Where did it start? Where did it start? 1. So where will it stop if I go backwards? 1. All I'm doing is taking the list in order, and then I'm swiveling it around and reversing it. That's all I'm doing. Okay? Why am I doing that? You might be asking yourself, which would be a very good question. Why is she doing that? Well, I want you to notice this. What happens when I add these two together? What do you get? N plus 1. What happens when I add these two together? You get n plus 1. What happens when I add these two together? You get n plus 1. What happens when I keep going down the list to every 2 numbers you add together? You get a whole bunch of n plus 1s, don't you? Okay, so on the left-hand side, I added the s here and this s here together, so this is 2s, right? 2 of those. And here I get a bunch of n plus 1s. Now here's your question of the day. How many n plus 1s do I get? N. How'd you get n, Jacob? Because it sounded good. Why would n be the right number? Why is it n? Jacob's right, it is n. How many numbers are in that blue box? There are n. I start at 1, I stop at n. Think of it with some concrete numbers. What happens if I start at 1 and I stop at 10? How many numbers is that? 10. If I start at 1 and I stop at 20, how many numbers is that? 20. Because I started at 1 and I worked my way up to the ending value. There are n of these guys. So there are n terms. Okay. I have n plus 1 added together n times. How do I shortcut writing that down? N plus 1 times n. It's times n. It's the same thing we did right here. C. N times is c times n. Repeated addition is multiplication. That's the reason we like multiplication, is because it lets us add things faster. I mean, that's really what it is. It lets us add things faster. So this is addition multiple times, n times. The way I get to add things n times together is I multiply by n instead. And then I'll divide by 2 to get the s by itself. So this s, this sum, is actually n plus 1 times n divided by 2. And that is the formula we're going to use over here on number 2. N plus 1 times n divided by 2. And just to make you feel really weird about this problem, the mathematician credited with this processing is actually a man by the name of Gauss. And Gauss figured this out with 100 numbers, not with n numbers, but with 100 numbers. He did this in first grade. He was 6 years old. Isn't that crazy? His teacher gave him a project, the classic project, to try to keep them occupied. Your teachers never did that, right? Just to keep you occupied. And told them that she wanted them to write the numbers, or to add up the numbers from 1 to 100 and figure out, and that should take a while. Except that he noticed a pattern, and he found the answer very quickly using this kind of a reasoning. Okay, this is the only one I was going to justify for you. Isn't that crazy? Yeah, it's the only one I'm going to justify for you. There's 3 more. I squared. So if you have I squared, the way that this one works is that you have the same n and n plus 1 that you have above, but then you also have times 2n plus 1, and it's divided by 6. This is one of those, we're gonna memorize a few things here. Okay, this is going to be one of them that you're going to memorize. And then the other, it's the only complicated one. The other 2 are very straightforward, very simple. Okay, they are everything that you would want to be true about constant multipliers, which is that the constant multiplier doesn't matter. It can be pulled out into the front of the problem. Okay, just like with derivatives and antiderivatives, the constant multiplier doesn't matter. And with sums and differences, also doesn't matter. We could separate this out and look at them individually and then add the sums of them individually together if that helped us in a particular problem. So everything we would want to be true about sums and differences and constant multipliers is. That's what this is saying. Okay, I'm going to do one example, and then we'll save the last example for next time, because then you don't have homework over both of them. Okay? All right, summation rules to compute the sum. All right, so what we notice here is that there's a subtraction sign, right? That's one thing we should notice. We should also notice that there's a 5 in front of the I. Everybody notice both of those things? Okay. That lets us change this problem and write it differently to use these rules. In particular, it lets us change it like this. I can pull the 5 out in front. I'll fill in the I equal 1 to 16 in a minute. And I can pull the I, the 5I, away from the 4. It isn't like I'm distributing, but it kind of feels like that, doesn't it? What we're really doing is we're breaking it apart. We are separating it into individual pieces. And both of these say I equals 1 to 16. Is everybody good with that? You might think, okay, why do I care? Well, you care because now this and this match the rules that we just came up with on the other side. That's why we care. They match. So the summation of I, which rule was that?
N plus 1 times N over 2.
It's the one I justified, right? It's the one I actually showed you where the formula came from Gauss. All right, so this should look like the 5 in front, and then N times N plus 1, or in the other order, divide by 2. We're going to put the N in a second, okay? That's what that looks like. Which one does the summation of 4 look like? The first one. And what does it say I should do? 4 times N, and my N always 16. So N in this problem up here is in fact 16. So if we go back in and we put in 16 here, then we will have the problem that we were looking for. So what does this become? A little bit of calculation there. What'd you get, Allison? 616. Do I have a second on that? Josh is checking. Mackenzie? Okay. 616 is correct. Awesome. Okay, and that was a lot easier than writing out 16 of these guys, wasn't it? It really is. Now I want to show you one thing to be aware of here that doesn't sort of appear very easily. We'll encounter this on number 3 next time, and we'll see how much you remember on Tuesday. Let's say we had the exact same thing, but it didn't start at 1. It started at 3. That's something different, right? None of these properties over here start at anything but 1. They start at 1. So what do? Well, what we do is we actually change it to start at 1. But if I did that, what did I really do to that summation? I added something in that wasn't there before. What did I add in? I added in what would happen if I plugged in 1 and if I plugged in 2, right? So the only way that I can put this equal sign here then is if I take out A1 and A2 from the problem. See, I have to change them, otherwise I can't use those rules. And I want those rules because that makes my life easier. So I want to change them, but I have to remove the pieces that I added in that didn't really exist there to begin with. All right, guys, with me? How would I find out what A1 and A2 are? Just plug in the number 1, find out what it is. Plug in the number 2 and find out what that number is. And I would subtract that from the sum. So this isn't like this, right? It's like this. I find all the sum stuff, which would be the 616 I just found out, right? And then I would take away the A1 value, which was 1 plugged in, and the A2 value, which is 2 plugged in. Okay? All right.